there were there were
That was
all of
my
these.
fault.
There were all these. Oh, we good? The
Yeah, we're
idea
good.
that Okay, cool. The idea that there are all these planets that could vary as much as the planets in our own solar system. And then, I start thinking about, oh, the potential for life. And we're at the stage where we can actually study these other worlds, these other planets. So, oops. These are called exoplanets. So it's short for extrasolar planets, and it just means planets that orbit other stars. And in our own solar system, we have a crazy diversity of planets. And there's no reason to think that these other systems would be limited to the planets, that's the types of planets that we have. But we found thousands and thousands of them. And before we really talk about exoplanets, it's important to get the vernacular right and get the way that we talk about planets, because we really use our solar system as a reference for these other systems. So, our solar system, everybody knows this. My very earthly mother just served us nachos, I guess, not 9 pizzas anymore. But here you can see all of our planets, and the scale in size is correct here. So this is how large and small the planets are relative to each other and relative to the sun. The distance is not right. The distance scale is off. But you can see from our solar system that everything is like, it's really uniform. Everything is everything orbits in the same plane. There's small planets that are closer. There's larger gas planets that are far. It's very, very organized, and very, very nice. Of course, you also have Pluto, which throws a wrench into things a little bit. It's way smaller than any of the other planets. You can see it compared to Alaska right here, which end to end, it's actually not as large as Alaska. It also has this really misaligned orbit. And that orbit, it comes inside of Neptune's orbit sometimes. So it's like very weird. It messes up the beautiful organization that we have, but there's an elegant solution for that, which is to just get rid of it. And obviously, Pluto is not a planet. It's a dwarf planet or a Kuiper Belt object. So when we think about exoplanets, these other planets that are orbiting other stars, the the terms that we use are related to the planets that we're familiar with. So small planets, roughly the size of Earth, we would call terrestrial or Earth-like planets. So whenever you hear Earth-like planet found by scientists or astronomers, it really doesn't mean much except that the planet is close to the size of Earth. It doesn't really speak to the atmosphere or there being water or it being habitable or anything like that. It's really just in reference to the size. Then we have the Jupiters or the gas giants. So this is going to be like Jupiter and Saturn. And we usually just refer to those as Jupiters. Then lastly, we have what are called the Neptunes. And these are also gas giants, but they're much smaller, much less massive than the Jupiters. And obviously, they're like much larger, much more massive than the terrestrial rocky planets. So, one of the main differences between the outer planets and the inner planets is just the amount of gas that they have. Now, one thing that we'll notice in this nice organization that I was talking about is that the Earth-like planets, the four inner planets, are distinctly separate from the four outer planets. And one of the sort of milestones or the markers in our solar system is what we call the frost line, and it's this dashed blue line here. So out beyond that line, you can have ices basically, but if you come in closer than that line, everything melts. You don't really get ices. So the thinking goes that the planets that are farther away are able to get much more massive because there's more ice. If you think about a handful of ice and a handful of gas, which one which one is gonna weigh more? It's the handful of ice, right? So if you just think about that, this sort of like first order thinking, if you are far away from your star, you can make a much more massive planet because there's just more stuff. There's more dense material out there that you can use. So, astronomers, we look at our solar system and we say it's likely that other systems are just like ours. We kind of use our initial data point to extrapolate and look for other planets. And to our surprise, the first types of planets that we found are called hot Jupiters. And they're these massive gas giants, these Jupiter-sized planets that orbit so closely to their stars that they complete an orbit in just 3 or 4 days. And so if you think about a year on a planet like this, it's only a couple days. And we didn't think that this was possible for the reason that I just said. Our thinking was that you had to form this planet far away. So why are we getting these hot Jupiters? How are these the first planets that we find? And it's still not totally clear the exact formation pathway or the exact pathway that these hot Jupiters exist. But there's really two ideas. One of them is, and this is at the bottom of the bottom of this plot here. One of them is that maybe you can actually form a gas giant close to the star. Like maybe that is possible, and we just don't fully understand how these gas giants are forming. Maybe there's multiple ways to form them. But the other way is that, if we are right, if you move to the top of the plot, maybe these gas giants do form far away like we think, but due to some sort of dynamical instability, they have like some energy injected into their orbits, and they get these really eccentric orbits that are very elliptical and less circular. And over time, the star will sort of rob some of the energy from the planet as it orbits around. And over a long enough time scale, you could start with a planet that's actually far away that ends up on a super close orbit like this. And when we realized that, we were like, okay, so we didn't even think these planets existed. But because they do, and they may be migrating in, perhaps we will never find small planets that are close to the star. Because if this migration process is so effective for giant planets, surely small planets would just kind of migrate into the star or get kicked out of the system. And then, to our surprise again, what we find is that the most common planets in our galaxy around sun-like stars are actually these smaller planets between the size of Neptune and Earth. We call them sub-Neptunes and super Earths. Astronomers are not all that creative in naming things, really. It's a sort of an elementary way to name these planets by their size. But most planets that are orbiting sun-like stars are these sub-Neptunes or super Earths, and they have orbits that are really less than 100 days or so. So less than the orbit of Mercury. Now that's interesting because if you think about our solar system, we don't have anything like this. And for me, this sort of like reminds me of this very human tendency that we have. And of course, you have it, scientists have it, everybody has it. Scientists are people. And what we do is we take this limited amount of data, like this one data point, our solar system, and then we extrapolate and we say, oh, everything, the other star systems must be similar to ours. And when we were wrong about it when we thought that there couldn't be hot Jupiters. We were wrong about it when we found the hot Jupiters and then thought that there couldn't be these small, close planets. So always something to keep in mind. Your personal anecdotal experience is oftentimes not representative of reality at large. But anyways, off that soapbox, we have found I think the number right now is closer to 5,600 exoplanets that we've confirmed. And it is a bit of a process to confirm a planet because you have to be careful about making sure that you're actually detecting a planet and you're not detecting some other variability or some wonky activity from the star or something like that. And of all the planets that we found, only about 4% are these terrestrial planets, these Earth-like planets, which I mean would mean that the planet that we're living on is actually pretty rare. One caveat is that it's hard to find small planets, and this is a pretty intuitive explanation. It's easier to find big things. It's hard to hide a Jupiter-sized planet that's right next to the star, but it is easier to hide a smaller planet that may be orbiting further away. So about a third of the planets that we find are these super Earths. About another third are closer to Neptune or sub-Neptune sized. And then a third are the gas giants, these Jupiter-sized planets. So we see that there's this really wide range of different types of planets that we're finding. And the group that we know the least about are the small terrestrial planets. Now, yeah, for me personally, the idea of having, Neptunes and Jupiters and hot Jupiters and cold Jupiters is all really interesting. But what really draws me in is the idea of life. And I mean, I don't know anybody who isn't interested in this. And here's this famous equation. It's called the Drake equation. It really helps you predict like the probability that there are other advanced civilizations. Not only is there life on other planets, but how many of those planets with life evolve advanced technology. So I want to walk through it because it's actually really interesting. And there are some things that we know very well about this equation, and there are other things that we don't know that well. So on the left side, this is the total number of technologically advanced, which we're gonna say we are. We're gonna say that the Earth has advanced civilization because we get to define. I mean, humans made the equation, so we get to define the terms. So we know that this number is at least one, right? Because we're here. It could go up higher than anybody could imagine, or it literally could be one. We could be the only ones. And all you have to do to like figure out exactly what that number is find the values of these terms. So the first one is the rate of stars that form, because every time you form new stars, you're going to form new planets. And we know the rate of star formation. This is something that we can observe. Like this is one of the terms that we actually know. Next, you go to the fraction of those stars that have planetary systems. And this one we know pretty well. We know just, again, from observing that sunlight stars average more than one planet. The exact average is like 1.1 or something like that. And the interpretation there is that stars average more than one planet. And like I said before, we're not that sensitive to detecting the smaller planets, the Earth-like planets, which may even be the more interesting ones. So that number could be much higher. We just don't know for sure what it is, but we have that lower limit of 1.1. Now, here's where we start to run into trouble. It's the number of planets in a solar system that have an environment where life could evolve. We could think of that as a habitable planet. And then the next one is, of the planets that are potentially habitable, how often does life actually arise and appear? So now we're getting into to a regime where we have no idea what the answers to these are. Fraction of life-bearing planets where intelligent life evolves. So it doesn't have to be technological. It could be crows, or octopuses are pretty smart, elephants, whatever. Then we have how many of those species actually develop the ability to like send out techno signatures, and then how long does civilization last? We don't know this one for us. We could be at the brink of how long civilizations last. I don't know. The United States is a little wild right now, or we could just be getting started, and have a long, fruitful future. I'm an optimist. Now, where we are right now in astronomy, of like what values we actually have the potential to start to get good information and constrain, are the number of planets that are habitable and that like may evolve life. This is where we're at right now. We don't really have much hope moving to the right quite yet, but here we can start to answer these questions. So first order thinking, you could just think of a habitable zone, also known as a Goldilocks zone. You've probably heard this term, but it's basically that stars are hot, and when you're closer to something that's hot, you get hotter. When you're further away, you get colder. And there's this nice range somewhere in the middle that we call the habitable zone. And this is an extremely basic and kind of reductive way of thinking about things because, in our own solar system, you could actually use this as a model for our own solar system. Mars is kind of in the habitable zone. It's on the outer edge, and Venus is in the inner edge of the habitable zone. But obviously, those planets are not suitable for life as we know it. Venus is way too hot. Mars is way too cold. And it doesn't have everything to do with the position. Mars is really cold because it doesn't really have an atmosphere, so it can't retain a lot of heat. Venus is really hot and it is close to the sun, but the reason that it's so hot is because it has basically too much of an atmosphere, has too much carbon dioxide, too many greenhouse gases that make it just keep getting warmer and warmer and warmer, and it can't really shed its heat like the other planets do. So it's not really enough to think about habitable zones solely as the position of the planet. You actually need to get a little bit closer and look at the atmospheres themselves. You could imagine swapping Mars and Venus, and Mars would get warmer because it was closer and it can't retain as much heat. Venus would go further away and it can retain a lot of heat. So you could easily imagine swapping those two planets and then potentially our solar system having three potentially habitable worlds. So what you really need to do is look at the atmospheres of planets. And that's what we do now. JWST, James Webb Space Telescope, is up there in space. And every once in a while, we'll look at a planet that transits in front of its star. So you imagine this is a Earth-like planet that we see in the habitable zone, and it crosses in front of the star. And what we want to do is this detective work that Gamal was talking about. And we can't go there, unfortunately. I can't check out the scene like a forensic scientist would do. But we do have some information that comes to us, and that information is light from the star. Now, the light from the star itself doesn't really matter. But you see that some of the light from the star is actually going to pass around the planet, and it's going to cut through the atmosphere, and then it's going to keep on coming to us. And lucky for us, the way that light works, some of those photons, some of that light that goes through the planet's atmosphere, it's going to run into molecules in the atmosphere, and those molecules will absorb some of that light. So when we look at the final picture of all the light that made it to us, it's going to be missing. It's going to be missing some light. You can really think of it as like a barcode, or maybe even fingerprints from the atmosphere of this planet. And here's an example of what an Earth-like planet would look like. You'd see some water features, you'd see some methane, carbon dioxide, oxygen. And if you saw all of these, then maybe you could say, hey, there's a planet that at the very least, I mean, it has water. We know that life needs water. There's oxygen. We know that life on Earth needs oxygen. And oxygen it's one of those things that's so reactive that when you find it, it is probably being produced. It's something is making it. Plants produce oxygen, but oxygen, it reacts with stuff quickly. That's why we breathe oxygen. That's why you need to keep breathing, like however many times a minute, because your body needs the extra energy that oxygen provides. And then carbon dioxide, that's obviously something that we breathe out, that we produce. So if you have all of these things, you can start to say, hey, here's a planet that is potentially habitable and potentially has life. It'd be tough to confirm for sure, and especially for smaller planets, because this is, you can kind of see it here. There's this slight gray outline around the planet, and that's, supposed to be the atmosphere. But for a planet like Earth, the atmosphere is really paper thin. Here's a picture of the Earth from space, and you can see that really thin, like white bluish glow. That's our atmosphere. And I mean, if you compare it to the size of the planet, you're really looking at something that is extremely thin. And we're trying to observe planets that are dozens, hundreds, thousands of light years away. It's not easy to test, to sort of differentiate between the photons that are going through that very, very narrow piece of atmosphere, compared to all the other light that's coming from the star. So astronomers really have our work cut out for us in this respect. But there's lots of people who are doing, work in creating and running theoretical models for what a potentially habitable planet, or a planet with a lot of carbon dioxide and water and oxygen, would look like. And there are plans within the next decade or so, as long as they don't get cut by NASA, because they love slashing NASA's budget. But there's this one observatory that's really interesting to me called the Habitable Worlds Observatory. And it'll be a telescope out in space, an observatory in space, that has the ability to actually take pictures of Earth-sized planets at Earth-like distances. So this would be amazing if it actually does end up being built, because we don't have that ability right now. Most of the planets, nearly all of the planets that we study, we don't have actual pictures of. We infer their existence indirectly by the transit method, like I was showing, where it blocks out a little bit of sun. And there are a couple other methods. So it's not easy, but technologically, these are things that we can do. And it's an extremely exciting time. And I guess the last thing that I want to leave you all with, everybody here is really interested in space and stargazing and learning about the cosmos and all the things that the universe has to offer. And we found 5,600 exoplanets, but we have never found an Earth-sized planet at an Earth-like distance from a sun-like star. So we've never even found an analogous planet to what we have here. And maybe that's because we're really special, really, really unique. Or maybe it's just because we're not sensitive enough to detect those planets yet. But that's something that, we'll all see in our lifetimes. That's a place that we'll all get to before it's all said and done. And yeah, I think that's the last thing that I wanted to share, but I want to open it up for questions. I don't think I got any. I wasn't checking the.
Yeah, that was my fault. I kind of lost track. There
Oh,
were
no,
three.
no, it's cool. I'll just start
I'll read
rambling.
them out. What is the size of the smallest exoplanet that has been directly observed?
So directly observed, there's not that many planets that have been directly observed. To me, like, a direct observation means that we took a picture. We covered up the star to block out some of the light and took a picture of the planet. It's called direct imaging. And there aren't that many planets that have been observed that way, but there are very small planets that have been indirectly observed. Like, you look at the star in this transit method that I'm talking about, you can actually see it right here on this graphic. The star has a little planet that's like right on the edge, and we can't zoom in and see this picture, but if you look at the star long enough, you can see it get a little bit dimmer. So you can infer that there's a planet crossing. Now, the smallest one that we have found, I believe, is very close to the size of Mercury, and it's a transiting planet. So it's one of these planets that crosses in front of the star like that. But it's about the size of Mercury. But it's really rare for us to find planets that small, because they're so small, they're hard to find. But about the size of Mercury.
That's great. Yeah, that was a great, thorough answer. And it's actually a great segue into the next question by Charlie Liu. Given the fact that most planets are much closer to their stars, does it mean most planets are too hot to sustain life?
That's a good question. That's a really good question. So there are actually a lot of planets that are much closer to their stars, as you said, but they orbit smaller stars. So in the realm of stars, the more massive stars are hotter. They have more fuel. They're fusing more hydrogen in their core, and they're just burning off hotter. So if you think about a small cool star, you can actually get much closer to it without getting too hot because it's not putting out as much energy. So a lot of the close planets that we have found are actually orbiting small, cool stars. And temperature wise, it seems like those planets could be within the habitable region. The problem that you run into is actually different with the smaller stars, and it's that they end up flaring a lot. um, Surely maybe you've seen these images from NASA of the sun with these huge solar flares that come off. It's just, huge filaments of gas that are coming off of the sun. And these small planets, or I'm sorry, these small stars do that a lot. So it's like, well, it's a cooler star, so you can get much closer to it and maybe be the right temperature for water, liquid water, or life. But if you're undergoing these immense flares all the time because you're so close to the star, then that could be something that sort of sterilizes planets or that erode, like blows away their atmospheres or something like that. So, a close planet could be too hot, but if it's a cool star, then it could be the right temperature. But you may have this other problem with just being too close to a star that's flaring and sort of hitting you with erratic amounts of high energy.
Isn't
Does that
that
make
amazing?
sense?
Yeah, that was a great answer. It reminds me of one of my favorite shows called Strange Place Called Earth. But anyway, yeah, that was a great answer. Next question from Jeanette McCulley. She asked about 10 minutes ago, so I don't know what you were talking about, but she asked, do habitable moons count in this equation? I don't know what you were talking about.
Oh, that's a good question. So I didn't even mention moons, but obviously we have a moon. And if you think about planets like Jupiter and Saturn, they have tons of moons, like hundreds. And I think right now Saturn is in the lead with over 100. They're constantly finding new ones. But I mean, if you just think about the diversity of moons that these gas giants have, then it's like, well, there's probably way more moons than there are planets in our galaxy. And, that could mean that it's possible that life may have a better chance of forming on moons just because there's so many more moons. The problem is that it's extremely hard to detect a moon. The ways that I've described that we detect planets, it's hard enough for us to detect small planets. It's even an added layer of difficulty to try to detect a moon that's orbiting that planet. It may be something that becomes easier as we get better at imaging the planets and actually getting pictures of the planets. But I could easily. Has anybody seen Avatar? It's one of my favorite movies, the blue ones, not the Airbender, but the tall blue
Yeah.
ones. They actually are on a planet that's, I think it's a little bit smaller than Earth, maybe eight. Sorry, it's not a planet, it's a moon. It's orbiting a big Jupiter gas giant. And that works. If you had if you had a gas giant that was in the habitable zone, now the gas giant wouldn't be habitable because it's all gas. There's not even a surface there, at least not habitable by our standards. But if you had a moon that was orbiting, it could absolutely be in the habitable zone. And it wouldn't surprise me at all if our galaxy is covered in moons that have life. That's a really good question. It's just so hard for us to detect.
Nice. Nice answer. And thank you for the question, Jeanette. All right. Now, Yothi Cherry. Just a comment. Wonderful talk, Dakota. You make
Thanks.
Overwhelming concepts, very digestible.
Nice, thank you.
I love it, Dakota. Yeah, and that's exactly the type of educational component that we want to bring to your vacation. So thanks, Yothi. We appreciate the comment. Back to Charlie Liu. How many total planets have astronomers found?
The number right now, I just checked it right before I hopped on here. It's 5,690, I want to say. You can actually hop on right now, pull up your phone, NASA Exoplanet Archive. If you just Google that, you can click on, there's a running counter. I think it's 5,600 and something. And that's confirmations. There's like several thousand more that are candidates where we think that we might be looking at a planet, but it just hasn't quite been confirmed yet. And that number is also in the thousands. So, potentially we could be looking at 10 or 11,000 planets or something right now that we know of. And this is truly is a tiny fraction of the actual number of planets. I mean, just using our number that we know of so far, this 1.1 planets per star average, there's 100 billion or 200 billion stars in the Milky Way. If they all have one or two planets at least, then we're talking about hundreds of billions or even trillions of planets in total. And so we're really looking at a tiny, tiny sliver of that total population.
And that's just our galaxy.
And that's just our galaxy. You would assume that all the other galaxies have the same, they have the same physics going on. So you would assume that they have the same sort of distribution of planets. Yeah.
Nice.
Big universe.
Yeah. Now, a question by Professor Jonathan Paul de Virviel. What is the difference between Cosmos with a K and Cosmos? I guess I'll answer that. Maybe that's for me.
Yeah, that's you.
Yeah, I'll put my camera. Seems like we can't both have the camera on at the same time, but Cosmos with a K is the root of the word. That's it comes from the Greeks, and it has meaning as well in terms of harmony and order. And so, to me, that's part of the resort as well. It's not just stargazing, the astronomy, but everything is connected, kind of like how we went over here, or did we discuss during. So that is, at least for me, what the meaning is for Cosmos with a K. And I would put an emphasis on the word connection, like connecting with yourselves, connecting with others, connecting with the Mother Earth. That's pretty big for me. Oh, I have heard that the search for life is focused on carbon-based life. Also silicon-based life as well. What are your thoughts on that?
Yeah, that's a good point. I mentioned this thing during the talk where we, focus our exploration from our perspective. We start from, well, we know what our planet is like. We know what the temperature is like. We know how much water is here. There's carbon dioxide. We know that on Earth, carbon is one of the most essential ingredients. And the reason for that has to do with the atomic structure of carbon. It's basically really good at making a bunch of connections. So you can sort of think of carbon as being this sort of all-purpose connecting molecule that will allow you to create all of the structures of life that we know of. And it turns out that there's relatively few molecules that share that characteristic with carbon. One of them is silicon. It's not quite as flexible as carbon, but it's flexible enough. If it's possible to have silicon-based life, the universe is so big that I'm sure that it exists. If it is physically possible. But And and people think about that. There are people who think about modeling carbon-based life, and think about what a planet with carbon-based life would look like from our perspective in terms of the things that we would actually be able to recognize. So, I think that when it comes to life, we absolutely have to keep our horizons wide, because we know what happened here, we know what works for us, but even with planets, we realize quickly that just because our solar system doesn't have certain types of planets doesn't mean that they don't exist. And it doesn't even mean that they aren't more common, right? So I think that it's like a wise business decision to think about and to look at life as we know it. But for sure, we have to keep our eyes open. Surely there's tons of different forms of life that we aren't even considering right now to be a possibility. And silicon based, people have considered it. If it can exist, it probably does. So those are my thoughts.
That's my answer too. Absolutely, Dakota. I agree with that one. Now, here's a good one I want to know as well. Michelle Smith, what is the topic of your thesis? What do you hope to do after you get your doctorate?
This is a good question. I'll try to keep this constrained because I can talk about this all day. So, uh, one aspect that I didn't really mention is that planets evolve over time. Like we live on Earth on these very short time scales where the Earth, when you're born and when you die, it really isn't going to be any different at all. But if you look on the scale of hundreds of millions of years, of billions of years, planets actually change a lot. When a planet first forms, it's going to be very different than when the solar system, whatever star system, has aged billions of years. And some of the ways that planets evolve are that they lose their atmosphere. We call it mass loss, and that's what I study. The different physical processes that cause planets to lose mass over time. And that's my dissertation topic. I'm kind of looking at different ways that or looking at mass loss for exoplanets from a few different angles. So my projects kind of look at it from like a current direct mass loss, looking at older systems and seeing if we can kind of backtrack how much mass they must have lost, and trying to look at young systems to see if they're losing more mass than the older systems. This is what the focus is for me. And after I get my doctorate, fingers crossed, this time next year, I really love doing the research and like asking the new questions and making the new discovery where I'm adding some value to the scientific accumulated knowledge. But I also really like doing this sort of thing, public education, public outreach on this. And this is why this is how Gamal and I actually got linked up, is because there's this like leisure and luxury aspect of the Cosmos resort, but then there's also this like wonderful education opportunity being underneath the stars in a dark sky region, and having telescopes, being able to look up and just study the universe. So a combination of those two things, the sharing what we learn with the public and with audiences of all kinds, but also doing the research and trying to figure out some of those things myself.
Great answer, Dakota. And I couldn't do the research myself, so I'm glad we got people willing to take a look at all those numbers and spend all that time doing the heavy lifting for the future of humanity.
You're welcome.
Thanks, man. And surprise, the last question which you answered, what do you hope to do after you get your doctorate? You're so right, Dakota. Nowadays, in the modern future, with astrophysics, you can do so much. And I love the hybrid that you got. So I will also be offering Dakota a position with us. So surprise to everyone. We hope to see Dakota more often as well. Awesome. So Karen Longblade, which is closest? And I guess Karen, you may have to ask again, but I'm guessing you mean which exoplanet is closest?
Yeah. So I'm assuming that that's what you're talking about. The closest planet to us on Earth is, it depends on the time of year, but Mars and gets pretty close. Venus gets pretty close. But you're probably talking about exoplanet. So it turns out that the closest star to us, Proxima Centauri, which is like roughly 4 light years away, actually has an an Earth mass planet. We don't know the exact size, but we know that the mass is very close to Earth's mass. It's also in the habitable zone of that star, but it's one of those small, cool stars. It's a low mass star. So the planet is much closer, but it just still happens to be in the habitable zone because the star is cooler. And that may be, yeah, I mentioned that it's hard to find small planets. It's harder to find Earth-sized planets. But this may be indicative of how common they actually are, because the closest star to us also has an Earth mass planet, an Earth-sized planet. And it's the closest star, 4 light years.
That's cool. You know what? I actually had always wondered that as well. So thank you, Karen. We got so many great questions. We do have to wrap it up at 9, so let's go to the next one. Because Earth currently has a magnetic field and Mars used to have one. Does that imply that magnetic fields are common amongst exoplanets? How would we detect such fields?
This is another really good question. Because the Earth's magnetic field plays in a huge role in the Earth being habitable. I'm in Southern California. If you remember, like a month or two, the Aurora Borealis, the Northern Lights, they came down really far, and people were seeing them actually across the entire United States, really low. And that is because there was this solar storm, a bunch of charged particles coming from the sun, and they are sort of like bullied our magnetosphere, this magnetic field that we have. And when those particles crash into our atmosphere, they light up green and purple and pink. And lucky we have that magnetic field, because if we didn't, these particles would just be clobbering our atmosphere, and they're really energetic. It's like bad for life. It's bad for DNA. So the magnetic fields are really important. The problem is it's extremely hard to detect something like that in another solar system. There's like not a great way to do it. Usually, when you want to detect a magnetic field on something that's far away from the Earth, and I'm not even talking about planets now, I'm just talking about other things like black holes, stars, this sort of thing. What you really have to do, or like the magnetic fields in galaxies, is think about the effects that magnetic fields have on other things. So we aren't really at the point to really analyze the magnetic fields for other planets when we can't even see the planet. It's hard to like see the space around the planet and see exactly how that magnetic field is interacting with either the solar wind or whatever else could be in the immediate environment. So what you just brought up is one of the huge unknowns for exoplanets, is what the other planets' magnetic fields are like. We can say something about our solar system, but it's very hard to make any determinations for exoplanets.
Good one as well. That was submitted anonymously, so thank you. Sarah Spitz, thank you for coming again to the second webinar, Sarah. I appreciate you. And Sarah, I think wants to get an answer, kind of like an opinion from you, like how spiritual astrophysicists are,
Mhm.
Perhaps you can give your opinion, like what do you think about like intelligent design, physics, dark matter, whatever the source, maybe of everything, even God,
Mhm.
intelligent
Yeah.
force to put it all together.
Yeah, it's a good question, and I actually get this one a lot. A lot of people sort of want to know, do physicists, astrophysicists, they tend to believe in God. I can tell you that I have colleagues that belong to every religion, that everyone possible. So it's definitely, it's not like you can't do both. It's not, you know what I mean? It's not that sort of thing. And feeling spiritual and connected is something that as humans we all have. And I think it's like, it's sort of, for me, it's sort of silly to write that off. I'm not personally a super religious person, but I can tell you with certainty that I feel like a deep spiritual connection to the universe and to the fact that the atoms that make you and me up literally were made in stars. Not like, it's not like a metaphor. We are actually made of things that had to have been made in stars. And there is like this real connectedness that I feel a very large, a very significant spiritual attachment. And that's not, you know, that's not really any different than the feel, the you know, the emotional, the spiritual feelings that we humans have with religion or any of the things that we believe. So, you know, my personal take is that I think in a lot of ways that feeling of being like connected to God or something higher, I feel that with the universe. So, you know, I can relate to that. But you know, it's a personal thing. So you really would have to ask people individually. And I think you would get a wide distribution of answers from astrophysicists.
Yeah, it would be really, yeah, that's a great question, Sarah. Even for myself, no astrophysicist here, but I do have an opinion. I'm visiting my mom right now. I'm in her room. You guys can see the cross. I definitely believe in God. Oh yeah, by the way, that's me and that's my sister. But yeah, we definitely were raised believing in God, and but it's also interesting, the concept of astronomy, and like you said, Dakota, I think the key word is connection. Thank you, Sarah. Oh, this is a cool one. Professor Jonathan again. Is there evidence of life on our moon?
To my knowledge, there isn't any evidence of life on the moon. You know, to really dig in, if you think about how we find the evidence of the earliest life on Earth, you really have to like dig deep into the geologic record, which physically requires you to dig deep into the Earth and like somehow get to those bottom layers. So, you know, I feel like it's not something that you could uh totally rule out that there's like something deep down, or maybe that there was a long time ago in the past. But to my knowledge, there's no evidence of life on the moon, on our moon.
There we go. I gotta be specific. All right. All right. Just a couple more. Kelly Stretzinger. For those who don't know, can you explain why Pluto got demoted from being a planet? Hmm.
Yeah. It's really straightforward. You know, categorizing Pluto as a planet was a case of mistaken identity. So what happened? It's super interesting. I know that I'm supposed to like breathe. I'm gonna go through as fast as I can. So we noticed that in the outer solar system, there were planets that were behaving as though there was like some other planet further. There was like some gravitational interactions that were going on, but we didn't know of any planets that were further. So we kind of assumed, well, there must be a planet out there. And they looked, and then we found Pluto. And we were like, oh, there it is. Like, that's the planet. That's the missing gravitational force that is, you know, impacting the other planets. But then we took a closer look at Pluto and we saw some weird things. You know, it has this weird inclined orbit. Um, it's really not that massive. It's not massive enough to have perturbed anything in the solar system in the way that we were observing. So it's not massive enough. It doesn't clear out. It has a weird orbit. It doesn't clear it out. There's other things that are close to the same mass and size as Pluto out there. So we realized that it doesn't really check as many boxes. It doesn't fit the definition. And then these are just definitions that, you know, a panel of humans came up with. It's not like written out in the physical laws of nature, but it just doesn't quite fit. But what's interesting though is we still have seen objects that have appeared to have been impacted by some really strong gravitational force, like a planet. So there is still this idea of Planet Nine, of some distant planet in our solar system that we just haven't been able to see yet, that is impacting things. It's just not Pluto.
And Amy Meyer asked earlier, or she stated, isn't it really dense and doesn't it have magnetic properties? So I think that goes along with what you were saying.
That Pluto's not that dense, actually. It's like 40 or 50% water in the form of ice. So it's really it's almost like a comet on steroids, maybe something like that.
Too bad it's probably a little too cold for us to live there.
Very cold out there for sure.
All right, all right, all right. We got so many great more questions, Unfortunately, we do have 3 minutes left, Who knows? We may do a series as well. But I did want to take a couple of seconds. A lot of people had questions, so we will definitely post these later on. But the Stargazing Center. So I mean, really excited to announce these to the community, and we are planning it for 2027. Essentially, it will be an on-site planetarium and observatory. So you guys can see here, featuring a lot of areas, including an interactive educational museum and a planetarium. And most, what I would say, cool of all, and what I really want to announce, and I'm super excited, is that we're currently working with a few consultants. We'll be working with Dakotah, and we'll be, you know, here's a great one as well. There was a great question from Colin Nichols. You're an astrophysicist, but do you ever do any visual astronomy yourself? I said, amateur or professionally? And you can answer that, Dakotah, if you want.
Yeah.
But I've actually,
Oh,
uh,
sorry. Go ahead.
but I've actually had that same exact conversation with my friend Raphael, who's also an astrophysicist with the George Mason University and working at the NASA Goddard program. And he's also part of the stargazing community. And that's something we discuss as well. It's like people and astrophysicists doing research sometimes are not even as close to the instruments as they used to be back in the day. And so Rafael and I were talking about how we see Cosmos as an opportunity for there to be a more of a connection between the research side of things and actually going out and taking a look at things or utilizing the instruments. But go ahead, Dakota, answer yourself as well. Do you do any amateur?
For sure. Yeah, I do have a small 4-inch telescope, and I do take it out sometimes. I have a camera as well, so I try to do a little astrophotography. I would say that I don't do it a whole lot. I have to get far away from where I'm at because I'm in LA. But yeah, I mean it's really you bring up a good point. It's not common to at this day and age, the telescopes that we use are like on top of mountains on the other side of the world type of thing. And so I don't really physically go there. I'll log on remotely online or something. But yeah, it's great to get your hands dirty and get a telescope and just go out there and look up.
Yeah, absolutely. It's always great. And wait, you know what is great as well? Um, Doing that in a class 2 Borel scale area. Yeah, so I'm really excited to let you guys know as well that that's, a big purpose in Cosmos. And how it relates as well, I want to tie it back to the Stargazing Center, is that we're looking to deliver a 1-meter telescope in aperture size. That'll be our main features of the observatory. So far, I've only seen that the Astronomical Research Group of Colorado, the Air Force Academy, has one. But besides that, I don't see any other larger telescope in Colorado. So we're very excited to host on site a stargazing center that will provide educational facilities for the community, for our guests, as well as for schools and for private parties to come take a look at the observatory, kids to learn about astronomy in an interactive manner with our trained astronomer led staff. And Yeah, we're really excited about all that. And since we're already past the 9 p.m. deadline, and I don't want to keep you all guys here, I'm very excited to finally end with the email, showing you the email that you'll be getting. It'll be a little different, but this is the email that you'll be getting on July 30th, and you'll be able to choose from all your stays. We've been getting a lot of questions, so we'll go ahead and make some of these public, but the idea is that you choose your villa, you choose your number of nights, and I'll actually show you guys. So the really cool thing is that only you guys, only the VIPs will be able to, and showing you a little bit behind the scenes over here. This is what the campaign will look like when you arrive there. And this will be for the general public with very little quantity, because most of our quantity and most of our availability is reserved for you guys that believe in us. And so in terms of booking, you're gonna get a secret link in the email. You'll just click whatever you want to book, whether it's 2, 3, or 4 nights. It's the Stargazing Villa or the Galaxy Villa. And oops, that didn't work. There we go. There we go. And you guys, you will have your secret link that nobody will be able to see this perk. It's only for you, and it's reserved for all Cosmos Stargazers. So very excited to show you a little bit behind the scenes. Dakotah, thank you so much for joining us today. And thank you for everyone that attended. I see we got a few more questions here. But yeah, we have a lot of great questions. We continue to be very excited to launch next week. And please email us at hello@cosmosresort.com. We're emailing back as quick as possible. And we're very excited as well to show you guys weekly progress of the construction. Like I said, I'm visiting my mom now, but I'll be back at the construction zone later this week. And I'll be showing you more videos of the Hamcrete as well as materials for septic and everything. So we're really, really excited to keep the Cosmos journey going. Dakotah, thank you for joining us, and see you guys soon, and definitely in 2025.
Yeah, thanks. Take
Bye.
care. Bye.
Thank you.